Hi, good morning, class.
Good morning, sir.
Sorry, there was a bit of miscommunication about the meeting link. And sorry about the background noise. There is some construction work going on. So I'll just wait for a few minutes for others to join and then we'll start the class. Can you all see my screen?
No, sir.
No. Can you see the PowerPoint now?
Yes, sir.
Mhm. Okay, I'm going to start the class now because we have 30 students online. So my name is Anant and I'm a new faculty in civil department. I did my PhD in Australia and then came back here to join as a faculty after doing a bit of postdoc in Australia as well as the US.
So you are not audible.
Yeah, so can you hear me now? Can you hear me?
Yes, sir.
Okay. So I'm sharing this course with Dr. Binit. Dr. Binit will be doing 2 lectures per week and I will be doing 1 lecture per week. So every Monday I'll be doing the lecture and I will be doing lecture on Unit 5, which is types of dams and their characteristics. And even in the end exam, I will be doing the questions from this unit. So this unit has multiple topics and we are going to focus on design of different types of dams. One is gravity dams and then embankment dams as well. Once we go through the designs of these dams, then we will look at spillways, types of spillways, and then energy dissipation below spillways. For the design of the dams, we are gonna look at different forces acting on the dams and then the failure mechanisms and how to design the dam safely to be able to withstand the forces acting on it. This is the lecture schedule for the Mondays throughout the semester from now on. The first lecture that we are doing is today on 26th. It's going to be an introduction lecture, an overview of the topics, and then a revision of some of the concepts from fluid mechanics and hydraulics or open channel flow. But from next lecture on, we'll start the design of dams. So I have created a Google Classroom. So I think all of you have access to Google Dashboard. This is the class code that you can add. Here I will be posting any announcements regarding the class, as well as the lecture materials from these lectures. These meetings are being recorded, so I will also put a link for the recorded lectures here. So I would suggest you to check this dashboard regularly so that you can keep up with the announcements. And before we begin, I also want to give you some suggestions on how you should approach engineering problems, not only in your exams, but also when you're designing something when you become an engineer. So when you're given a design problem, you should always start with a sketch and then make sure you show all the annotations, solve the problem as much as possible symbolically before you insert any numbers. So in the exam, if you get a question on design of dams, I would expect to see that you solve it symbolically throughout and then put the numbers in the end. So if you just write the numbers and give me just the answer, I'm not going to consider that. So I want to see that you solve it symbolically throughout and then insert the numbers at the end. To give you an example of how I would approach a problem, I want to share this. Can you see my screen again? Yes, can you see it?
Yes, sir.
Okay. So let's say this is an example where you are requested to find out the elevation difference between 2 points 1 and 2 in a pipe flow. So you have a pipe, which let's assume it has circular cross section, and you have flow from left to the right. And I have 2 points 1 and 2 between which I want to estimate what is the elevation difference. Now, for this
Dr.
problem,
Anand,
yes,
I would like to tell one thing that here's that question is not visible, right? So please make that slide
yeah.
visible.
So this is an example, so it's not an actual
Yes,
question.
yes. Now it's okay. Yes.
Yeah. So now let's say I asked you to find out the elevation difference between points 1 and 2. I have shown you a pipe sketch, and then I have also indicated where the points 1 and point 2 is. I have indicated the flow direction, and then I begin my solution by stating that I'm applying the Bernoulli principle between points 1 and 2. So I know where point 1 is, where point 2 is, and I'm stating that I'm applying the Bernoulli principle between points 1 and 2. So Bernoulli principle is that energy is constant, the total energy is constant. So energy at point 1 should equal to energy at point 2 if there are no losses in the system. Now, if you recall the Bernoulli principle, so it has 3 heads, which is the pressure head, velocity head, and the elevation. So the elevation, sorry, just give me a moment. I'm applying this Bernoulli principle on the left-hand side at point 1 and on the right-hand side at point 2, which has the same pressure head, velocity head, and elevation. Now I am solving it for difference between the elevations Z1 and Z2 symbolically. So I arrive at this expression. And then here I would insert the numbers at this stage. And then I would get the elevation difference to be some XX meters. So always remember that you always show the units. If you do not show the units, then we don't know what you're talking about. It could be 5 millimeters, or I can assume it to be 5 meters, or I can assume it to be 5 kilometers. So always make sure that you always write the units. So that is how you should solve any question in the exams. Now moving forward in the presentation. So this is an introduction to the dams, and we are going to talk about dams throughout the every Monday lecture. So a dam is a structure that is built to restrict the flow of surface water. So for example, it could be for a purpose to reduce flood flows to the downstream sections. So if you build a dam, you're creating a pool of water, which is the reservoir, that would prevent the flood to the downstream sections. Or it could be to draw water for water supply from the reservoir, or it could be to draw water for irrigation purposes. And also we can use the water that you store in the reservoir to generate hydropower And in India, hydropower contributes to about 12.3% of power generation capacity. A reservoir that you create by building this dam could also be used for navigation and aquaculture. So if you're fish farming, then you can also use the dams. Now, why is it important to design a dam properly? If you do not design a dam properly, then it is going to be breached or it is going to fail, which will result in a huge loss of population as well as property. Now, these are two recent examples. Like in 2021, there was a lot of flooding in Andhra Pradesh, which caused the entire dam Annamaya project to be washed away in the flood flows. And recently, again, there was a dam, Tista Dam, that got washed away. And this would result in human loss, which we do not want to happen to anyone. So the main reasons for failure of dams is insufficient design. So when you consider the forces acting on the dam, and if you do not ensure the stability of the dam, then it is going to fail. And also because of improper construction practices. So on plan, you might have done a proper design, but when executing it, if the field engineers are not aware of how to execute it properly, then they are going to do what they know, and it is going to lead to failure of the dams. And in extreme cases, the dams could be so in some extreme cases, the dams could be designed for, let us say, 1 in 100-year return flow, but the actual event could have been 1 in 500-year event. Then the inflow is much higher than the design inflow for the dam. So it is also going to cause failure of the dam. If the dam is not designed for earthquake forces, then it's going to fail. Even if the dam is not properly maintained, for example, you have sluice gates which open and shut when there is a flood flow. If they are not being maintained properly, then the fluid is going to exert forces on the gates, which can cause the failure of the gates itself and then overtop the dam. This can also cause the failure of the dam. So in this unit, you are going to learn about how to design a dam properly so that you can ensure it is stable under the design flow conditions. So nowadays you can actually do the dam failure analysis using computational fluid dynamics, which is CFD in short. So these are computer numerical models which consider the physics of the dam breaks or dam failures and then give us the predicted overflow or the predicted flood discharges at downstream locations. So here you can see an example of a dam being breached and the flow from the dam is discharged into the downstream channel. So this you can simulate using CFD nowadays. So you don't have to do complete analytical or theoretical analysis of the flow conditions. Now talking about dams, there are different types of dams that we are going to look in this unit. So the one is gravity dams, the second is earthen dam, and then we have rock-fill dam. So gravity dams are usually made of concrete. So the way they are they are stable is based on the self weight of the dam itself. So you have multiple forces acting on the dam, but they are all being resisted by the self weight of the dam itself. So that's why they are called gravity dams. And then you have earthen dams where the material being used is more than 50% of the material is soil. And in rock-fill dams, more than 50% of the volume being used is either rocks, boulders, or cobble. So it's not soil. So it's going to be more coarser material. And you can see the pictures of two examples of gravity dam, which is Bakranangal Dam, and then you have an earthen dam, which is Tehri Dam. And towards the end of this unit, we are going to look at spillways, which are structures that are designed to release flow to the downstream sections of a dam or a reservoir. There are different types of spillways that we are going to look at. So one is Augie spillway, which is the regular spillway that is in the top picture. And then you have I think this is a duct spillway where the water is being drawn into a duct and then released on the other side of the dam. This is the chute spillway, which is built on one dam where the water is being discharged. And then you also have step spillways, which are built to dissipate the energy efficiently. So we are going to look at all these types of spillways in the coming lectures. Now, so that's the introduction of this unit on what we are going to learn. Now, from next lecture, we're going to look at the forces acting on the dams and then how to design dams. Before that, I want to do a bit of revision of fluid mechanics and open channel flow hydraulics, some of the concepts that you might be using in the design of the dam. So let's switch to that now. So let's start with the basic concepts in fluid mechanics. Let's start with the hydrostatics. Let's say you have a tank as shown in this figure, and you have points 1 and 2. So the pressure at point 1 would be atmospheric pressure. So in our calculations, we consider gauge pressure, which is with respect to or relative to atmospheric pressure. So our P1 is 0. If you talk about absolute pressure, then P1 is not 0. But we are talking about gauge pressure. So it's with respect to atmospheric pressure. Now at point 2, which is at a depth of h, the pressure is going to be gamma h. So gamma is the unit weight, which is density times gravity multiplied by the depth h. Now the units of pressure is Pascal, so that's important to represent. So you can derive this pressure at point 2 by applying the Bernoulli equation or the energy equation between points 1 and 2. So as I said, I'm applying energy equation between points 1 and 2, where we have the total head on the left-hand side should be equal to the total head on the right-hand side. And if you just rearrange the terms, then P1 is 0 because it is atmospheric. You don't have any velocity in the tank because the flow or the fluid is stagnant or static. And then you don't have velocity at point 2 as well, so that becomes 0 as well. So all of the terms become 0 except Z1 and Z2. So the elevation difference between Z1 and Z2 is h. So your pressure P2 becomes rho GH, that is minus gamma h. Now, what direction is this pressure acting in? So the hydrostatic pressure acts equally in all directions. So at point 2, the hydrostatic pressure is going to act equally in all directions. So that's hydrostatic pressure. Now imagine you have a channel or an open channel, and the water is up to certain depth as represented here. And you have an obstruction like a gate or a dam. Now, what is the hydrostatic pressure distribution going to be on this dam? So as I said, the pressure at the surface is going to be 0. The pressure on the bottom is going to be proportional to the height h. So the pressure here is gamma h. So the pressure is linearly increasing from 0 to gamma h. So and on this wall, the pressure is going to act, and it is increasing linearly. Now, what is the hydrostatic force corresponding to this pressure? How do we calculate the hydrostatic force on this vertical gate? So we know pressure is force times area. and force simply becomes pressure multiplied by area. So what we do is within this hydrostatic pressure distribution, you consider a small elemental area with a pressure small p, which has a width or a height of dh. So this has a height of dh. So the total height of the dam is big H, and the width of this small elemental area is small dh. Now, according to force is pressure times area, your dF would be the pressure acting on this element, small p, multiplied by the area of this small elemental, which is dA. Now, to get the total force acting on this gate, you just integrated integral of dF, and then you integrate the pressure multiplied by the small dA. So you have to integrate between 0 to h. So your total force would be an integral of 0 to h. The pressure at this point is gamma h if you consider the depth to be h. And then the width or the height of this small elemental area is dh. So the area would be the width into the paper multiplied by dh. So that is bdh. If you just integrate this, you would get the force acting on the force acting on the total wall would be half rho g h square multiplied by the width of the wall into the paper. And the units of the force are Newton. So again, always remember to mention the units of force or pressure or depth. So whatever quantity that you calculate in the question or the problem, or even if you design a dam, always make sure you represent the units. So this is the horizontal force acting on the gate, half rho g h square multiplied by the width of the wall or the gate. Now, moving on, we will look at the fundamental conservation laws that you are going to keep using in your open channel flow and the design of dams, or anything that you talk about open channels, you are going to use these three conservation laws. So one is conservation of mass. Let's say you have a pipe and the flow is from left to right. So whatever the flow enters this pipe should leave this, as long as there is no storage. So the flow in must equal flow out. So the flow, by flow we mean the discharge Q1 should equal discharge Q2. And the discharge is represented by the cross-section area of the pipe multiplied by the velocity V1. So you have A1 V1 on the left-hand side at section 1 should equal A2 V2 at section 2. So this is our section 1 and this is section 2. And then you have conservation of momentum, which states that the time rate of change of momentum equals the sum of external forces. So if you have a channel which is reducing in width as you go along, or a pipe which is reducing in width as you go along, then you have the velocity changing between U1 and U2, A1 and A2, P1 and P2. So this is the rate of change of momentum, rho Q multiplied by the change in velocity. That would equal the total forces acting on this control volume if you consider a control volume. And then third principle that you are going to use is conservation of energy. So the conservation of energy states that the total energy is constant. So if you know the energy at a point 1 and there are no losses between point 1 and 2, then the energy must be conserved. So you have three heads: pressure head, velocity head, plus the elevation, which is constant throughout the system if there are no losses. And then, so that's a revision of fluid mechanics. And then let's look at some of the concepts in open channel flow. One is specific energy. So earlier we have seen the total energy in a pipe system is pressure head plus velocity head plus elevation. But so this is for pipe flows. But for open channels, what we say specific energy is the sum of hydraulic head plus velocity head. The hydraulic head simply represents the depth of flow. So let's say this is the channel bed and you have a flow to a certain depth. If the depth is y, then so that is the hydraulic head plus velocities. So plus the velocity head. So this specific energy is constant. And critical depth is the depth that flow would achieve when the specific energy is minimal. And that is usually represented by DC. And you have uniform flow. Uniform flow is when you have a channel that is sloping and then the free surface is parallel to the channel bed. So here the forces are in balance. So you have the weight of the fluid acting downwards and then frictional or shear resistance, they are in balance. So that is why you do not see a change in flow depth. So if the flow depth is constant in the channel and the flow velocities are constant, then it is uniform flow. And then you have gradually varying flow. When you have changes in the channel configuration, then you would see the flow depths to change. Let's say I have a channel and then there is a drop at the end of the channel. Then the flow is not going to be horizontal, not going to be parallel to the bed, but it is going to change. So you have a change in flow depth as you come towards the end of the channel. So this is gradually varying flow. And then you have rapidly varying flow. For example, if there is a merging of two flows, let's say you have a channel where on one side you have higher depth, which is subcritical flow. And then on the other side, you have a supercritical flow with a lower depth coming in. You have a hydraulic jump to lose energy. So this is rapidly varying flow because the flow conditions are changing within a short distance. Whereas in gradually varied flow, the flow conditions would change in a longer distance. And then you have a concept of Froude number, which is ratio of initial forces to gravity, and you would get velocity v by root gh. So if Froude number is less than 1, then this is subcritical flow. And if this is more than 1, then this is supercritical flow. And if that is 1, then that is critical flow. So when you have a supercritical flow joining a subcritical flow, what you would see is hydraulic jump. And a hydraulic jump forms to lose energy because you have a transition between high energy flow to low energy flow. Then you have depths D1 and D2, which are called conjugate depths. And you can derive the relation between D1 and D2 as a function of the Froude numbers. So when you apply the energy equation between section 1, let's say I consider this section 1, and I consider this section 2, then if you apply the energy equation between 1 and 2, you can derive a relation between the depths D1 and D2 as a function of the Froude number. So these are called conjugate depths. So these are some of the concepts that you might be repeatedly seeing when we talk about open channel flow, and especially in design of dams or irrigation canals. So this is all for this lecture, and I'm going to upload these notes on the Google Classroom. You can download it from there, and as well as I like upload this lecture recording after discussing with Dr. Binit. And next week we don't have class on Monday because you would have mid-semester exams going on. So we have to catch up with one of the lectures that we missed last week. So we had a lecture on 19th, which was not conducted. So if you go to Google Classroom, I have a link to a poll which would take you to a poll where you can choose your preference for this class. So the class that we missed on 19th, you can choose which one you want to do on these 3 dates, and then we will schedule it for that day. After that, after the mid-semester exams, we will resume as usual according to the actual timetable given in your class schedules. But we just have to catch up on this lecture that we missed, which is on the 19th of February. So when we reschedule this lecture, we are going to start on forces acting on dams and then the methods of analysis. From there, we will move on to factor of safety and failure modes for dams. So any questions on this so far?
No, sir.
I'm going to share this link to you in the chat box right now, so you can vote which one you would prefer.
So also share the Google Classroom code so we can join the Google Classroom.
Yes. Yes. So those are the links. You can join the classroom. Just let me know if you're not able to do it. And I'm going to also write my email here, so you can contact me on my email.
So the chat box is not accessible.
How is it?
Because sir, we are not in the team. We joined via link.
Okay. So, okay, I will add you on the Teams, all of you, and I'll put it on the Teams as well. I'll add all of you in the Teams. That's okay. And my office is in first floor of civil department in the environmental engineering lab. So if you want to discuss anything, you can come to my cabin as well. So I'm usually there between 9 to 5. Any other questions for today?
Sir, just out of curiosity, what are
Mhm.
the maintenance practices for dam that we have to look for?
So one is to make sure the gates are operational. So the sluice gates, if you do not, let's say, maintain them, they can get rusted over time. And then when the actual flood event is happening, you won't be able to open the gates. Then the fluid forces would break the gates and that would overtop the dam. That would create more dynamic forces on the dam itself. Or if you have sedimentation in the reservoir, you should keep desilting the reservoir so that the capacity of the reservoir is not reduced drastically. So these are some of the things.
Okay,
Yeah.
sir, thank you.
No problem. So any other questions?
No, sir. Thank you, sir.
Okay.
So
All
from
right.
where
So
you
we will catch. Yes, go ahead.
Sir, I was asking for the resources you just told about. Where from where we can have those? Because
So
I'm
first I
not
will add all
getting.
of you on Teams, and then on Teams I will share the link for the Google
Okay,
Classroom.
okay. Grateful, sir.
Yeah.
Thank you, sir.
Yeah. All right. So yeah. So if there are no other questions, then that's all for today. We'll catch up in the next class.
Thank you, sir.
All right. Thank you.
Thank you,
Thanks
sir.
for joining.
Thank you, sir.
Thank you. Bye.
Bye, sir. Thank you.